Hi everyone. In this lesson we are going to go over alternating series and conditional convergence. So to start with, let's take a look at alternating series. So here's a definition. An alternating series is a series in which the signs of the terms alternate between plus and minus. And this pattern is usually created by including a term like -1 to the n or -1 to the n plus 1 in the series. So let's take a look at a few examples here. Consider this series. The summation of -1 to the n plus 1 divided by n. So you notice that -1 to the n plus 1 term. That's going to create the alternating sign pattern for us. So this series, if you write out a few terms, this is what you get. Let's just notice how we get this. If we put 1 in for this n, notice that you get -1 squared over 1, and of course -1 squared is 1, so that's how you get the +1 right here. Then if you put 2 in for this n, you get -1 cubed over 2, and -1 cubed is -1, right? And so that's how you get the -1/2. So you notice that negative right there. So we went from plus to minus. Then if you put 3 in for the n here, you get -1 to the 4th over 3. -1 to the 4th is +1, so you get +1/3. And let's do one more. If you put 4 in for the n, here and here, you get -1 to the 5th over 4. -1 to the 5th, since this is an odd power, this is going to be -1 over 4, and so you get -1/4. And then you'd get +1/5, -1/6, and so on. So you see how that -1 to the n plus 1 power is creating the alternating sign pattern. Now here's another example here. Now in this example we start out with n equaling 0 instead of 1, so you'll see that oftentimes. So we have -1 to the nth power times 3 over 2 to the n power. Now that will create this series: 3 minus 3/2 plus 3/4 minus 3/8 plus 3/16, and so on. So let's just do a few terms here. Notice if we put 0 in for the n, we get -1 to the 0 times 3 over 2 to the 0. And remember, by convention, any number to the 0 power is 1, except if a is 0, of course, then you have an indeterminate form. So what we get here is 1 times 3 over 1, so that's just your 3 right here. That's how you get the 3. Then if you put 1 in for the n here and here, you get -1 to the first power times 3 over 2 to the 1. -1 to the 1 power, well, it's just -1, so you get -3/2. Then if you put in 2 in for the n here, of course you get -1 squared times 3 over 2 squared. -1 squared is 1, so that gives you +3/4. Then if you put in 3 for the n, you get -1 cubed times 3 over 2 cubed. So that's going to be -3 over 8. And so you see how this -1 to the n is giving you this alternating sign pattern. Okay. Now let's take a look at this result that we have here. Now this is a very important result when we're working with series. This is called our alternating series test. So let's consider this. Now our alternating series test makes this statement. We start out with a non-negative sequence of numbers, and we consider an alternating series like either this one or this one. So with this series right here, you notice we have -1 to the n plus 1 times a sub n, and we go from 1 to infinity. So that's going to create the pattern a1 minus a2 plus a3 minus a4, and so on. The -1 to the n plus 1 is going to be creating that pattern. Or you could put -1 to the n, in which case you'll get the pattern -a1 plus a2 minus a3, and so on. So just a slight difference there. That's all. So that difference comes from changing the exponent from n plus 1 to n. Okay, now if we have these two conditions down here, if these two conditions are met, then both of these series that we have up here will converge. And the two conditions that we need for convergence of these two series are this. We need the limit as n goes to infinity of the an to equal 0. Okay, that must be met. And also, we need that the sequence of an's that we started with has to be a non-increasing sequence. Okay, so we need, notice that we have a sub n plus 1 is less than or equal to a sub n. And you need condition 2 to hold for n sufficiently large. That is, for little n larger than some fixed number like 1,000 or 10,000. This condition doesn't have to hold for the first few terms in your sequence, but once you get to a certain point, like say 10,000, then it has to be met from there all the way to infinity. Okay, so that's our statement of the alternating series test. Once again, just to quickly summarize here, if you're given a sequence a sub n of non-negative numbers, then either of these two alternating series that you create will converge as long as the limit as n goes to infinity of the an's is 0, and the a sub n sequence is a non-increasing sequence for n sufficiently large. Now, we'll take a look at a few examples first before we consider the proof. So let's look at these examples. So here we want to determine if this series, -1 to the n plus 1 over n, converges or diverges. Now let's notice that if we write out a few terms of this series, putting 1 in for n, we get 1. Putting 2 in for this n, we get -1/2. 3 in for n, +1/3. 4 in for n, -1/4, and so on. So it's forming this series, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on. So does this converge or diverge? Well, we have to identify what the an terms are for this series and try to apply the alternating series test. So you notice that we can write that as okay, so there we go. That's how we can write it in a little different format. So we identify the 1 over n as being the a sub n terms that are used in the alternating series test. So those are the a sub n's. So we need to see if those two conditions of the alternating series test are met. So first of all, is it true that the limit as n goes to infinity of the a sub n's, is that equal to 0? Well, let's see. The a sub n's are the 1 over n. Well, yes, of course, that is 0. So condition 1 is met. Now condition 2, we need this, at least for little n bigger than some fixed constant. Well, let's consider this up here. So is it true that 1 over n is bigger than or equal to 1 over n plus 1? Is that true? Well, yes, of course that's true, because if you start out with 1 over n and you make the denominator a little larger, like we have right here, that will make your fraction a little smaller. So actually this is true. We have something a little stronger than this. We actually have this, of course. Strict inequality there, because over here the denominator is a little larger than this denominator, so you certainly have this holding, so this does hold. Now another way to see that is if you just consider the function 1 over x and you differentiate it. Notice that this function is negative for x greater than 0. So that means that the function 1 over x is a decreasing function. Okay, so this simply tells you that 1 over x is decreasing for x greater than 0. Therefore, you will have this holding. Okay, and so therefore, we can conclude by the alternating series test that this series actually converges. So we'll just put that up here, that this series converges. And once again, all we had to do was verify that the two conditions of the alternating series test held. So the limit of the ANs was equal to 0 in this case, and it was also true that AN is bigger than or equal to A sub n plus 1, because this holds, or by looking at the derivative of 1 over x, verifying it's negative, that means that 1 over x is decreasing, so that means that this will hold as well. Okay, now this is an interesting series right here. Just note this as well. So note that if we look at the series 1 over n, right, recall that that is 1 plus 1/2 plus 1/3 plus 1/4 and so on. This series actually diverges by the p-series test, right? The exponent here is a 1, and if you think back to the p-series test, for p less than or equal to 1, this will diverge. Okay, so this certainly diverges either by the p-series test or the integral test you could use. So this series diverges, but we found that using the alternating series test that a slight modification of this that this series actually converges. Okay, so you see this series was not an alternating series and it diverged, but when we made it alternating, now it actually converges. So that's something important to take note of for this harmonic series right here. The harmonic series diverges, but if you make it alternating, it actually converges. Let's take a look at another example. Now in this example, we want to determine if the series -1 to the n plus 1 times n over 2 to the nth power converges or diverges. Now the -1 to the n plus 1, that's going to create an alternating sign pattern. So if you write out a few terms in your series, you'll see that this is what you get. For example, if you put 1 in for the n here, you get -1 squared times 1 over 2 to the 1 power. So that's how you get the 1/2. If you put 2 in for this n, you'll get -1 cubed is negative, so that's how you get the -2/4. Of course, that's 1/2. We just didn't simplify it. And let's just do one more. If you put 3 in for the n, you'll get -1 to the 4th is +1 times 3 over 8. So that's how you get the +3/8. And then you get -4/16, or 1/4, of course, +5/32, and so on. So let's see if this converges or diverges. So we have to identify what the AN terms are here to use the alternating series test. So let's just notice that we can write that series. We'll just put it right here. Okay, so these are the AN terms that we're working with. So in this case, the ANs are... Now let's determine if the two conditions of the alternating series test are met. Well, if we look at the limit of our AN terms, we have to do that one first. Okay, so we have to evaluate this limit. Now you notice that this is of the form infinity over infinity, right? N is going to infinity, and 2 to the n is also going to infinity. So we can actually use L'Hopital's rule to evaluate this. So now I'm not going to put x's in place of the n's. I'm just going to differentiate these with respect to n. So we get limit. Derivative of the top is 1. Derivative of the bottom is the natural log of 2 times 2 to the nth power. You have to remember that the derivative of a to the nth power is the natural log of a times a to the n, right? We went over that previously when we were discussing differentiating exponents. Now as n goes to infinity, of course you can see that since this term right here goes to infinity, that our limit here is 0. So yes, condition 1 is satisfied. Now condition 2, we have to show that this is true, or determine if it's not true. If it isn't true, then we can't apply the alternating series test. We would have to try to do something else. So we want to verify this. Holds. Well, if we consider this function, let's differentiate this and see if it's negative. That'll mean that this is a decreasing function, so this will certainly hold then. So if we differentiate this, let's see what we get. Bottom times derivative of the top minus top times derivative of the bottom divided by the bottom squared. Now when I square this, we're going to get 2 to the 2x power, right? Now this is equal to, we can factor out a 2 to the x in the numerator and then cancel it with one of the 2 to the x's in the denominator. In other words, we can write it like this. Let's just move up here, put it up here. So we can write that as all right. Now 2 to the x divided by 2 to the 2x, well, that's just going to be 1 over 2 to the x power, right? Or you can think of rules of exponents. This would be 2 to the x minus 2x times 1 minus x times ln 2. All right, and you just get okay, just like that. Or you can just realize that this 2 to the 2x down here you can write as 2 to the x times 2 to the x, of course, and one of these will cancel with that one. So that's just another way to see it there. Okay? So anyway, what we have now, if we consider this function that we have right here, for x sufficiently large, you should be able to see that the numerator up here is going to be negative, right? Because eventually 1 minus x times the ln of 2 will be negative, right? As x gets larger and larger, this term will be dominating the number 1, of course, and this will be negative. In particular, it'll be negative for x greater than, if you were to simplify this inequality, this will hold for x greater than 1 over the natural log of 2, of course. Okay, and that is approximately 1.44. So you see this will be negative right here. Let's just put it right over here for x bigger than or equal to 2, right? So therefore we have that this is negative for x bigger than or equal to 2. And so therefore this will hold for little n sufficiently large. Okay, so we've just determined that conditions 1 and conditions 2 are met. Therefore this series converges. And once again, we did that by verifying that the limit as n goes to infinity of the an's was 0. We did that using L'Hopital's rule. And then we verified that a sub n is bigger than or equal to a sub n plus 1 by verifying that the derivative of this function, we just replaced the n's with the x's. We verified that the derivative of this function was negative for x sufficiently large. And that means that this will hold for little n sufficiently large. And so by the alternating series test, we have convergence. Let's take a look at another example. Let's consider this one, the summation from 1 to infinity, negative 1 to the n times n plus 1 over n. Now for this one, if you look at this, now for this problem, let's identify what the ANs are. Well, we can pretty easily pick off that in this case the ANs are like that. Well, we see right away that condition 1 is not going to be satisfied here. If we look at the limit as n goes to infinity of n plus 1 over n, this is equal to 1, right? That does not equal 0, so we cannot apply the alternating series test. It doesn't tell us immediately that we have divergence, but it just means we can't apply it. Okay, well, let's also notice that since the limit as n goes to infinity of n plus 1 over n is 1, what that means is if we just look at the limit as n goes to infinity of the whole thing here, throw in the negative 1 to the n, you see these terms right here, put the n right back in there, these terms are approaching 1. This is creating an alternating pattern. So these terms are going to be oscillating between values that are very close to negative 1 and 1. So it'll be as if this series is going negative 1, 1, negative 1, 1, negative 1, 1. So we see that this limit does not exist. And since it does not exist, it most certainly is not equal to 0. Therefore, this series diverges by the nth term test. And we are finished. So we see that this series diverges. So once again, we tried to apply the alternating series test. We saw that condition 1 was not met. So then we looked at it again and saw that, well, the limit of these terms is not 0. So therefore, by the nth term test, we actually have divergence. Now here we want to take a look at the alternating series remainder theorem. Now if you think back to the previous examples we've just done where we use the alternating series test to determine convergence or divergence, we never actually found what the series were equal to. We only determined if they converged or diverged. Well, this theorem will allow us to approximate convergent series. Even though we may not know exactly what they converge to, we can at least determine how many terms we should take in the series to get within a certain degree of accuracy of the actual answer. So the alternating series remainder theorem makes this statement. If we're given a convergent alternating series, so we assume that this is convergent, and it converges to the number s. And we also need, just like for the alternating series test, that the ANs are non-negative and they are non-increasing. Now for this test we do need it for all n, not just for n sufficiently large. It does need to hold for all n that you're considering. Then the remainder, which is the difference between the true sum from 1 to infinity and the nth partial sum, Sn, satisfies this inequality. So it satisfies this right here. So the difference between the actual sum from 1 to infinity and just the nth partial sum, where you sum from 1 to n, the difference between those two in absolute value is going to be less than or equal to your n plus first term coming from the an sequence. So that's our alternating series remainder theorem, and what we can do is we can use this fact to determine how many terms we should take in our approximating sum. In other words, how big should this n be, so that we're within a certain desired degree of accuracy of the true answer s. That's how we can use this inequality. Now let's take a look at this example before we consider the proof of this theorem. Now in this example, we want to determine the number of terms, capital N, needed so that the nth partial sum of this series, so the sum from 1 to capital N of this series, negative 1 to the n plus 1 over 2 to the nth power, approximates the true sum from 1 to infinity of that series to within 0.0001. So in other words, we want to find out how large should this capital N be so that this number that we can calculate is within 0.0001 of this number. So that's what we need to do. Now also notice that this series, if you write out a few of these terms, it's this alternating series, 1 minus 1/2 plus 1/4 minus 1/8 plus 1 over 16 minus, next one would be 1 over 32 and so on. Notice that the denominator here is 2 to the nth power, and so that's why you have these terms 2, 4, 8, 16, 32, 64, and so on. All right, now we need to determine how large does this n need to be. Well, let's recall this inequality right here from the alternating series remainder theorem, right? Okay, now we need to identify what are our a sub n terms from this series? Well, if we look at that series, notice that we can write it like this. All right, so these are the AN terms in that sequence. All right, so what we do now from this inequality that we were told is true from the alternating series remainder theorem, what we're going to do is we're going to set this less than the desired level of accuracy. So we're going to set this less than 0.0001 and solve for that capital N. And then once we solve this inequality for N, for capital N, well then we know that that capital N will satisfy this inequality then. It'll certainly satisfy this, and then we'll have our answer. Okay, so to do that, that's exactly what we're doing right here, notice. So a sub n plus 1, that's going to be 1 over 2 to the n plus 1 power. We set that less than 0.0001. And now we need to solve this for n. Okay, well, that's just a simple inequality to solve. Multiply the 2 to the n plus 1 over to the right. Divide the 0.0001 to the left, and you end up with this right here. Okay, just notice that when you divide the 0.0001 underneath the 1 over here, you get 1 over. All right, and that's going to be 10,000. Okay, this is 10 to the negative fourth right here. And so 1 over 10 to the negative fourth is 10 to the positive fourth, and that's 10,000. So that's how you get that. And of course, just multiplying both sides here by 2 to the n plus 1, that moves over to the right-hand side like this into the numerator. Okay, and now we just have to solve this for n. So right here we have the n is in the exponent. We need to get it out of the exponent. So remember, the way you do that is you take the natural log of both sides, right? So if we take the natural log of the 10,000, that is certainly going to be less than the natural log of 2 to the n plus 1. Drop this n plus 1 out in front of the natural logarithm, and so you're going to end up with this side equaling now just divide the natural log of 2 underneath the natural log of 10,000 over here to move it over to the left-hand side of the inequality, and you end up with this line right here. Subtract 1 over to the other side, and there's what our n should be. Our n should be chosen to be larger than the natural log of 10,000 divided by the natural log of 2 minus 1. And if you evaluate the left-hand side here, you'll find that this quantity is approximately 12.29. So we should choose capital N to be larger than 12.29, and so we can pick n to be 13. So 13 or larger will guarantee that the nth partial sum is within 0.0001 of the actual solution S. Now let's just take note of one other thing with this example. Now the series that we were given is actually a geometric series, so we can actually exactly evaluate what the capital S should be. So let's do that and compare it to our 13th approximating sum. So if we evaluate let's just note that we can write this as a geometric series, so it actually can be written like this. Like that. Notice we just took one of these negative ones away, so we have an n in the exponent here and an n in the exponent here, and now we can write that as, put that negative out front there. And now you see this is a geometric series that starts at 1, not 0. It starts at 1, with the r equaling negative 1/2. Now if you think back to the geometric series that we studied previously, if you start your sum at 1 and go to infinity for a geometric series like this, r to the nth power, that's going to equal r over 1 minus r. Remember, if you start at 0, then you would have a 1 in the numerator here. Okay, but we're starting at 1, so we have r over 1 minus r. So this is going to equal negative, that negative right there. The r is going to be negative 1/2, so it's going to be negative 1/2 divided by 1 minus negative 1/2. So that's going to be negative 1/2 divided by 3/2. Now if we simplify this quantity, cancel the 2's, negative, negative, give us a positive, you'll get 1 over 3, or 1/3. And that's what the s is equal to in this case. So s is actually 1/3. Now if we compare that to s sub 13, the difference between these two numbers should be less than 0.0001. And if we calculate that, now s sub 13, we have that evaluated right here in the notes. So we sum from 1 to 13 of negative 1 to the n plus 1 over 2 to the n, and you get this value right there. You can double check that using a calculator or computer. And if you calculate this, you'll find that you get this value right here, 0.0000407, and that is certainly less than 0.0001. Notice we have 4 zeros here, 3 zeros here, so this number is less than 0.0001, and that is what it should be, right? If we did everything correctly, the difference between these two should be less than the error that we wanted, and it is in this case.